Okay, everyone, let's get started. Good afternoon. It's our great pleasure today to have Professor Jerome Darbon to give us a talk. So Professor Darbon is an associate professor of applied mathematics at the Brown University. He's currently on leave from CNRS. His current research interest includes faster algorithms for solving high-dimensional Hamilton-Jacobi partial differential equation and optimal control problem, image processing, and optimization algorithms. Jerome, please.
Thank you very much, Hongji, and thank you very much for the invitation. Today, I'd like to give a talk about some recent efforts that I've been doing at Brown with my graduate students, Tingwei Meng and Gabriel Provencher-Langlois, that is about solving Hamilton-Jacobi PDEs in high dimension using neural network architectures. So let me give you the canonical problem that we have for when we solve those PDEs. So you are given a PDE of the following form, when S is a function from Rn cross R into R, H is a Hamiltonian, and J is an initial data, and we want to solve for any X and T at PDE. That PDE arises in many applications, such as optimal control, imaging sciences or data sciences, or when you want to control unmanned aerial vehicles or cars and so on. The key point here is that in order to solve this guy, you really need to solve it in practice for high dimensions, n. And here could be millions if you are dealing with digital images. In application involving control of drones, then n is still high but much reduced, say 15. And the whole point of this PDE to solve those applications is to be able to evaluate not only the solution at any given x and t, but also the gradient. Once you have access to these two informations, then it means you are able to solve the optimal control problems, certain imaging sciences problems of the optimal trajectories of UAVs. For applications, n is big. So we need to solve this PDE in very high dimension. As I mentioned again, in imaging sciences, n could be millions, but for optimal control problems, n is more or less around 12 to 16. Of course, we want fast algorithms, but we also need algorithms that requires very low memory and low energy because we want to do those computations for embedded systems. And that connects to applications where you want to optimally control a drone or a car in real time, and you have those constraints about low memory and low energy. There have been many approaches to solve this PDE of type Hamilton-Jacobi PDE, and perhaps one of the most well-known schemes are based on a grid-based approach, and they have been developed originally by Stan Osher at UCLA and Shi-Wang Xu at Brown University, and they are known about ENO, WINO, and discontinuous Galeckin methods. They have many excellent properties. They can deal with a wide range of Hamiltonians, but they require to discretize space and time, and it turns out that the number of grid points you need to solve this PDE using this discrete scheme is exponential in n. In practice, it means that these numerical approximations are not doable when n is larger or equal than 4. If it works for 4, then you go to 5, and then you will need terabytes of memory. That behavior about the difficulty of computing solutions of Hamilton-Jacobi PDEs is known as the curse of dimensionality. That is a term coined by Richard Bellman. So there have been many approaches to mitigate or to overcome the curse of dimensionality. So one of the approaches that have been quite successful in the last 15 years is known as the max plus method. You have a more recent work involving tensor decomposition methods, or sparse grids, and model order reduction. And a few years ago, with Stan Osher, we developed optimization schemes to compute, using optimization techniques, solutions to certain of these Hamilton-Jacobi PDEs. And there are many other approaches trying to overcome or mitigate the curse of dimensionality for these Hamilton-Jacobi PDEs. Recently, one of the new trends to try to solve those PDEs in high dimension relies on some machine learning and neural techniques. So the key idea of using machine learning or neural network for solving this PDE essentially relies on a powerful theorem that is known as universal approximation theorems for neural network that tells you that if the solution lives in a good functional space, then you can always find a neural network that will be able to approximate that function in that class of functional space. So that's the general trend that we observe in using machine learning and neural networks for solving PDEs. It is based on this theorem. One of the drawbacks of using neural network is that most of the time they are black box, and it is hard to interpret what the neural network is doing, and that may lead to a problem of generalization and also reproducible results. But nonetheless, the key idea of this research are based on using the universal approximation theorem. In this talk, I'm going to consider neural network for solving certain Hamilton-Jacobi PDEs, but I'm not going to use any kind of universal approximation theorem. I'm just going to exhibit conditions on neural networks having certain architecture, and I will give you conditions on the parameters of the neural network and show that these neural networks are actually a representation of the solution of the Hamilton-Jacobi PDE. There is no approximation. There is another advantage for using neural network, and that is from a computational point of view. Because of the huge success of machine learning and neural networks for many applications beyond PDEs, many companies have proposed new hardware designs, new silicon designs for implementing this neural network, not on usual processors, but on dedicated hardware. The key word here is FPGA. It's a new class of silicon designs that have been originally proposed in the 80s, and now they are used more and more by big companies like Intel, AMD, Xilinx, and they provide new designs to efficiently implement neural network using those new chips. What you gain by using this new way of doing computations is that you have a more precise meaning of what is fast. You can reduce the latency of the computation. It means you can reduce the amount of time you need to wait to get an answer, or you can also increase the throughput, which is the quantity of evaluations you get per second. And more importantly, those new chips, FPGA-based, have very low energy requirement. To give you an idea, when you have an FPGA and you can do the computation on that FPGA, you are using essentially 100 times less energy than on a usual CPU. So these chips are well suited for embedded system, but also for cloud servers, because you are going to use much less energy. So it means the electricity bill will be much lower while still maintaining an excellent performance. In order to achieve this implementation using this new hardware, then you need to use new softwares that are available from those companies. And those softwares are also available on the cloud. For instance, on Amazon, you can use FPGAs and the associated software on the cloud using Microsoft or Azure. You have the hardware and the software to program those guys. You can also buy boards. I can show you how they look like. I have one here. It's a little board, and the FPGA is that little chips that you see here. And you can program them using softwares programmed by provided by these companies. The main requirement is that all your numerical schemes requires to be expressed as a neural network. So we need to change the way we think about computations. It's not about mathematical operations involving linear algebra and some of the mathematical techniques. We need to represent solutions or quantities that we want to evaluate numerically as neural networks. And once you have this neural network, then you program it using this new software, and then that software generates the code to run on this dedicated hardware. So one of the main questions of this effort here is how we can leverage these computational resources, dedicated hardware, for solving high-dimensional Hamilton-Jacobi PDE. That question can be reformulated as finding mathematical conditions that certify that a class of neural network actually compute a viscosity solution of a given Hamilton-Jacobi PDE. The way we're going to approach this problem here is by drawing mathematically new connections between neural network architecture and representation formulas of Hamilton-Jacobi PDEs. And so I'm going to give you two examples of two classes of Hamilton-Jacobi PDE for which we can exhibit neural network architecture that are capable of representing exactly the solution of the corresponding Hamilton-Jacobi PDE. Once you have this result, it gives some light, it sheds some lights on some of the physics associated to the Hamilton-Jacobi PDE that can be actually encoded or hardwired in the neural network architecture. And we shall see that the parameters of the neural networks and the activation functions define both the Hamiltonians and the initial data. So there are no approximation because these neural network architectures compute exactly the solution of the Hamilton-Jacobi PDE. And when the function is differentiable, it also gives you for free the gradient with respect to space of the solution. And these results allows you to interpret some of the neural network architectures in terms of solutions of Hamilton-Jacobi PDE. So we can leverage the knowledge that we have on those PDEs and transfer them into the architecture of certain neural networks. And as I mentioned before, all these results do not rely on any universal approximation theorem of neural networks. We just draw an exact representation between the solution and the neural network architecture. Do you have any questions? Feel free to interrupt me. All right, let's go on. So the outline of the talk is a first architecture to represent solution of certain Hamilton-Jacobi PDEs that are inspired by a variational representation of the solutions that is known as UPF, the UPF representation formula. And then I will show you how we can borrow the idea of the UPF representation formula to create a first neural network architecture to solve certain Hamilton-Jacobi PDE. Then I will give you another architecture that is inspired by the Lax-Oleinik representation formula, and I will give you some properties of what we can do using those neural network, and then finally I will draw some conclusions and tell you what we are working on right now. So let's start with a first architecture. And the class of Hamilton-Jacobi PD we're going to consider here is of the following form. It's perhaps one of the simplest one in the sense that the Hamiltonian H depends only on the spatial gradient of S. And you are given an initial data J, and I'm going to assume in this work that J is convex so far. And if you assume some continuity assumption on H, then it is widely known that the viscosity solution of this Hamilton-Jacobi PDE written here can be written as this following optimization problem involving H, involving J star of P, where J star of P is the functional transform of J. And it reads as follows: J star of P is exactly the supremum of X in Rn of the linear form Px minus Jx. So this formulas is a variational formula for that gives the solution of the following Hamilton-Jacobi PD. Now, we can get inspired by those formula and creating a neural network that looks like as follows. Here I give you a shallow neural network. It means I have only one internal layer that is given here. The input of the neural network are X and T, where I want to evaluate the solution. From the input, I am considering M neurons, and each neuron is taking the input xt and doing an affine combination of the inputs using the parameters pi, theta I, and gamma I. So this is classically what a neuron is doing. It computes an affine combination of the inputs and produce a result, and then we combine the results of all these neurons using a pointwise maximum, and that defines an output of the neural network that I'm going to denote by f evaluated at the input xt, and that is a real number. So this is perhaps the simplest, or one of the simplest neural network architecture. It's not a deep one, it is a shallow one, only one layer of M neurons followed by an activation function that is called in the neural network architecture max pooling. And that neural network architecture gives you a function f with variable x and t and parameters pi, theta I, and gamma I. And this is the mathematical representation of what this neural network is. The question in terms of Hamilton-Jacobi PDE is to identify the class of Hamilton-Jacobi PDE for which the F defined by the neural network is a viscosity solution of. So it means we need to find conditions on pi, theta I, and gamma I to find what is the initial data and what is the Hamiltonian, so that F is a viscosity solution of the corresponding Hamilton-Jacobi PDE. In order to do that, we need some assumptions. So I have three sets of assumptions here, A1 to A3. The first assumption, A1, is simply an assumption that I make for the mathematical analysis, and I say that the parameters pi needs to be pairwise distinct. In practice, it doesn't matter if the pi's are not distinct, it just simplifies mathematically the analysis, but it has no impact on the result. Then I also have A3, which is a technical assumption that tells me that each neuron in the intermediate layer does contribute to the solution. And again, this is a mathematical assumption that we do here to simplify the analysis. In practice, if you have a neuron that never contributes to the solution, it's fine. It will not change the result. However, A2 is a very strong assumption where I ask for the existence of a function g such that every time I evaluate that function g at the parameters pi, it has to give me gamma I. So I ask a relationship involving the convexity of a function between the parameters pi and gamma I. Given this assumption, then we can exactly create the initial data and the Hamiltonian from the parameters. So what I have here is the neural network that defines the function f. I simply define the initial data j as f evaluated at 0. So it means I'm going to remove the term t times theta I, and that gives me a function that I call j that I want to see as the initial data. Using the assumption that I had before, I know that the function j is going to be convex, and I can compute the Fenchel transform, and you have a representation of the Fenchel transform that is as follows. And if you consider the set of minimizers in the representation of the Fenchel transform of j, then you can create a Hamiltonian that reads as follows. So you always have a representation formula of the Fenchel transform of j that involves an optimization problem. You consider the set of minimizers of this optimization problem, and you use them to define the Hamiltonian H. So you have representation formulas for J, J star, and H. And all those functions are given from the parameters of the neural network, pi, gamma I, and theta I. Then you can prove the following theorem, that if the assumptions A1 to A3 hold, then the neural network that we consider with the parameters that are given by theta I, and gamma I, defines the function j and h that I gave in the slide before. And you can show that f is actually the unique, uniformly continuous viscosity solution to the following Hamilton-Jacobi PD. So it means that once you have this neural network architecture, that is a shallow, fully connected, shallow network, and the activation function is the max pooling. Then you assume A1 to A3. Then from the parameters pi, theta I, and gamma I, you define the H and J, and you know that the neural network architecture, neural network, define the function f, and you are actually evaluating the solution of the following Hamilton-Jacobi PD. You can also show another result, that the same f, it means the same neural network that defines the function f, is also the unique, uniformly continuous viscosity solution to another set of Hamilton-Jacobi PDEs, H tilde, where H tilde agrees on the H that was defined above for each pi, and otherwise they have to be greater or equals than H evaluated at P. So H tilde is another function that you can see as a Hamiltonian, and what you ask is that they agree with H on the pi, and otherwise the graph has to be above the graph of H. So it means you can talk about the pointwise smallest Hamiltonian for this neural network architecture that solves the Hamilton-Jacobi PD. So the summary So this architecture so far is as follows. You are given the following shallow neural network that defines the function f. We show that that neural network actually computes a viscosity solution for h and j given by the parameters of the neural network. And you do not have uniqueness of the Hamiltonian. You have many possible Hamiltonian, but among all possible Hamiltonians, the h that was defined is the smallest one in terms of the pointwise minimum. It is required for this architecture that the initial data is convex, but the upshot that you get is that h may not be convex. H, for instance, can be concave, and that's totally fine for this architecture. And also, if you want to compute the gradient, then the gradient is the element that realizes the max in the max pooling when the solution is differentiable. If the solution is not differentiable, you get a viscosity solution, then you have several candidates that are given by the neurons that gives the max in the max pooling activation function. So here I just want to give you an example of how you can solve some Hamilton-Jacobi PDE. So I'm just giving you a set of parameters for the pi, theta I, and gamma I that defines an initial data that is here the L infinity norm in Rn, and h is given by the characteristic function of the L1 ball in Rn. Then we can invoke the theorem and claim that the neural network with those parameters is actually the viscosity solution with the Hamiltonian H given here and J here. You can also show by using the second point of the previous theorem that this neural network is also a solution of the following Hamilton-Jacobi PD, and it's the unique viscosity solution. So you can also have different examples where here I give you another initial data, another Hamiltonian, and you can have explicit formulas for the parameters of the neural network. And then when you set the parameters this way, you compute the solution, the viscosity solution of the corresponding Hamilton-Jacobi PDE. So here we did the computation for n equals 6, but for representing the solution, I only represent a two-dimensional slice of this 16th dimensional solution space, and I show you this function, only the 2D slice of a high-dimensional Hamilton solution of a Hamilton-Jacobi PDE. So this is the initial data when t equals 0, and this is the solution that you can compute using the neural network architecture. And I want to highlight that this is indeed a viscosity solution. The solution is not classical because you see kinks in the level sets. And what we get here is an exact solution using the neural network without error up to the machine precision that you are using to implement the neural network. And you get the very nice discontinuities that we keep seeing here. You see kinks in the solutions, and the numerical scheme that we propose here exhibits these kinks as it is expected by the theory. And this is the graph of the solution for a different time. I just want to briefly mention here that we can change this previous architecture where we replace the max pooling by the neuron that realizing the maximum. So the only difference is that instead of considering the maximum of all the neurons, I retain one of the index that realizing the maximum. and I'm going to call this new architecture where I just change the activation function max by arg max as gradient of f with respect to space. So we can show that actually this neural network architecture computes the spatial gradient of the solution of the Hamilton-Jacobi PDE. In physics, it means you have access to the momentum, and that neural network defines a function u that is given by equation 8. You can have an analog of the previous results that works for dimension 1, and that gives you a connection with the 1D conservation law, and you can show that this neural network is actually the unique entropy solution of the following conservation law. And as before, the flux that you have here given by the gradient of h and is not unique. You have an infinite number of possible flux, and all you ask for this theorem to hold is that the Hamiltonian H tilde needs to agree with the original Hamiltonian for each pi, and otherwise you need to you ask that they are above the Hamiltonian up to some constant c. The result here is a simple application of a theorem proved by Da Fermos and the Division of Applied Mathematics in the 70s. You can have, again, a variation of this architecture where we keep the same input, the same shallow structure, but we replace the max pooling by what we call a smooth max pooling. The definition of the smooth max pooling and the associated function defined by the neural network is written here. So when epsilon goes to 0, then this this f epsilon converges to f in the sense of gamma convergence. You can specialize what some of the parameters theta will be. We force here another relationship between the coefficient, the parameter theta I and pi. So you get that kind of neural network architecture that gives you this definition for the function that is implemented by the neural network. And you can prove that the neural network that you created satisfies the following Hamilton-Jacobi PDE with a second order term involving the Laplacian of the solution with respect to the space variable. And here you have the initial data that is given by this function. And it is a very classical techniques to show that when epsilon goes to 0, then the solution of this Hamilton-Jacobi PDE, it means epsilon here will go to 0, you converge to the classical solution. I want to summarize what we have so far. So far, we have been able to exhibit a class of neural network architecture that represents viscosity solution of certain Hamilton-Jacobi PDE, where both the Hamiltonian and the initial data are given by the parameters of the neural network. So we show that we have a natural Hamiltonian that is the smallest possible Hamiltonian, but the neural network is also a viscosity solution of an infinite number of different Hamilton-Jacobi PDEs. But I insist that we have a natural Hamiltonian that is given by the smallest one. You can find all the details and the proof in that paper. And one of the questions that we have here is, can we design other neural network architecture that are able to solve different kinds of Hamilton-Jacobi PDEs? And the answer is yes. We're going to use another representation formula for certain Hamilton-Jacobi PDEs known as Lax-Oleinik formula and we're going to get other kind of architecture. So let me present briefly what's going on here. I again consider the same Hamilton-Jacobi PDE, when the Hamiltonian H depends only on the spatial gradient of the solution, but I ask here H to be convex. Before, in part 1, we were asking J to be convex. The Lax-Oleinic representation formula tells you that under the assumption of convexity for the Hamiltonian, plus some technical assumption involving the continuity of J, you can write the solution of the above Hamilton-Jacobi PDE as an optimization problem. And this is the usual way to represent the solution of this Hamilton-Jacobi PDE using the Lax-Oleinic formula. And by using a change of variable, you can also write it this way. I write these two formulas because these two formulas gives me idea about creating neural network architecture. And I will have two classes of neural network architecture, one being inspired by the first formula and the other one inspired by the second formula. So it's classical in convex analysis to denote the Fenchel transform of the Hamiltonian as a Lagrangian, and so I'm going to use L for Lagrangian that is defined as the Fenchel transform of H. So let me give you first another class of neural network architecture that is based on the first formula. So I still have a neural network where the input is X and T, and the output of the neural network will give me a real number that I call F1 of XT. Here I have two layers for this neural network. The first layer is taking the input X and T, and first we compute X minus UIT. And we have M neurons that are computing these quantities when UI is a parameter of the neural network. The L function, the Lagrangian, that is the Fenchel transform of H, is an activation function that we use right after the first operation. And at the end of the first layer, we have evaluated L at several points, X minus UI over T, when UI has some parameters of the neural network. And then we take these outputs and we simply add some constants AI, and then we finally do a mean pooling. So when you are implementing this neural network, mathematically, you are considering functions that can be written as follows if the minimum of I, when I is the number of neurons in each layer of the following quantities. And we have that the initial data can be represented as an optimization problem involving what is called in convex analysis the asymptotic function. So we know how to represent the initial data using some convex analysis tools about this function when t equals 0. And what you can prove is that this neural network architecture, when L is convex, because H is convex, then you have that F1 is the Lax-Oleinic solution of the convex Hamiltonian that is given by the Fenchel transform of L. So it means the activation function here, L, gives you the Hamiltonian by considering its Fenchel transform. And then the initial data can be expressed using the concept of asymptotic functions in convex analysis. So here is a technical remark that says that although we assume J to be in the following form, it's actually in practice not so restricted because you can show that J is actually dense in a set of what we call reasonable initial condition. And I refer to the paper that I will give you in a few minutes for the details of what we mean by that. Okay, I can give you, again, examples about what those neural networks can do. So here I consider the dimension n equals 10. I only consider 3 neurons per layer, and I can consider the following activation function L that gives me the Hamiltonian, that is the characteristic function of the N2 ball in Rn. You can set some parameters UI, and this is the initial data that you're going to consider. So it is the pointwise minimum of 3 quadratics that are shifted in space by UI and then along the y-axis by AI. And so that neural network, once you fixed these parameters, gives you a viscosity solution for the corresponding Hamilton-Jacobi PDE when H and J are given by the parameters of the neural network and the activation function. So here I show you the initial data of the solution in dimension 10, and as before, I only show a 2D slice of the solution. And this is the solution when t equals 1. The theory tells you that you do not have a classical solution for this Hamilton-Jacobi PDE. You need to have a viscosity solution, and that can be seen because you have kinks in the level sets of the solution, and we see that the neural network is capable of capturing those kinks and shocks without any problem because it satisfies the theorem that we saw before. And this is for another t and another t. The second architecture inspired by the Lax-Oleinik formula is as follows. As before, we are given x and t as the input of the neural network. The neural network will give me a real number, and I have 2 layers here. The first layer is first computing the quantity x minus tv, and tvi, when vi is a parameter of the neural network. Then I consider the activation function that I call here j tilde, that gives me those quantities, j tilde evaluated at x minus t times vi, and I shift this quantity by t times bi, when bi is another parameter of the neural network, and again I take them in pooling. That neural network architecture gives me the definition of the following function that is implemented by the neural network, and we want to know if this guy is a viscosity solution of a corresponding Hamilton-Jacobi PDE. And the answer is yes, under an assumption that is similar to what we covered in the first part of this talk. We need to assume that there exists a convex function little l, such that every time you evaluate L at the parameters of the neural network Vi, it equals the other set of parameters of the neural network Bi. Then it means, again, that you have the following function that is implemented by the neural network. And assuming that j tilde is a concave function, and that the assumption above is satisfied, then you can show that the neural network is the Lax-Oleinik formula for the Hamilton-Jacobi PDE where the initial data is given by J tilde, that is the activation function that we used, and the Hamiltonian is given by the parameters of the neural network, Vi and Bi, using the following optimization problem. So you can prove several properties about the viscosity solution of this Hamilton-Jacobi PDE. For instance, that the Hamiltonian has to be piecewise affine and convex, and then that J has to be concave. So I can, again, consider examples where we have here dimension 10, 3 neurons. I consider the following activation function that is minus 1/2 of the L2 squared of x. When I set these parameters Vi, then that gives me the following Hamiltonian. And I can plot the solution, and as expected by the theory, we do not have a classical solution. The solution is not differentiable, but we are able to consider, to compute without error, the numerical viscosity solution of this PDE. And those are other examples for different times. And let me skip that example, and let me do the summary here of what we have so far. So far, we have 3 neural network architecture. The first neural network architecture was inspired by the up formula. And the two other ones are inspired by the Lax-Oleinic formula. And in this table, we can see the properties that are required for the Hamiltonian H and initial data J for each architecture. So for the first architecture, we require H to be piecewise affine, and the initial data to be also piecewise affine and convex. For the second one, we require the domain of H to be convex with bounded domain, and the initial data takes the following form, where L prime infinity corresponds to the asymptotic function of L. And I remind you that this specific class of the initial data is not so restrictive in practice because they are dense in many problems that you consider when, for instance, optimal control problems are considered. The second architecture involving the Lax-Oleinic formula requires the Hamiltonian to be piecewise affine and convex, and the initial data to be concave. So you can get all the details as well as the proof in that paper given below. To conclude, I want to mention some properties that these neural networks have. They can indeed overcome, in certain cases, the cost of dimensionality, because when n goes large, and I gave you example, for instance, n is 16, then we can still evaluate efficiently the solution of the corresponding Hamilton-Jacobi PDE. However, what we did not cover here is that if you consider a Hamiltonian that cannot be represented by the following architecture, then you need to put more and more neurons in the layers, and M may go to plus infinity. And so you do not suffer from the curse of dimensionality, but you are going to suffer for the curse of complexity. You need to get a neural network that becomes larger and larger in terms of neurons. So far, I mean, in this presentation, we only focused on the approximation error of the solutions, meaning here actually the error is 0. Now, you may want to consider learning the Hamiltonian and the initial data from observed data, And we did that in the first paper. And actually, the results that we obtained for recovering the Hamiltonian and the initial data from some data sets are not conclusive. The results are not that great, and we suspect it's because it involves solving highly non-convex optimization algorithms, and we've been using the usual solver for neural network, the Adam optimizer, and it does not do a good job at all for minimizing the loss function involving this data. So we hope, and we're still trying to pursue this idea that we could understand and interpret certain neural network building blocks in terms of solutions of Hamilton-Jacobi PDEs. And we hope that by pushing those correspondences, we may be able to to leverage the theoretical knowledge we have on the solutions of Hamilton-Jacobi PDEs and translate them into neural network architecture. In this talk, I only presented 3 architectures, but we've been working in extending those approaches to cope with more general Hamiltonian and more general initial data. And in particular, we have some unpublished results that show that we can create some neural network architectures that computes actually the viscosity solution for certain Hamiltonian with a space dependence. So this is a joint work with Peter Dower at the University of Melbourne in Australia and William McInerney at UCSD, and we hope to have the first paper out in the next few days. I didn't present here some numerical results in terms of speed involving FPGA, and it's because we didn't finish the implementation yet, but hopefully we'll be able to do that over the summer. And these are the 2 references that in which you can find more details about the material that I covered here today. Thank you very much.
Thanks, Jerome. Very nice talk. Any questions so far? Audience? I do have some questions. So just to sort of clarify my understanding. So far seems like there's no training involved because for the specific choice of the initial data, you basically solve the equation. So as you sort of mentioned in the conclusion page, right? So if you have you sort of call it a seamless problem. If I give you some given equation and give you some given data, have sampling, that I can imagine you use whatever expression with your J as a neural network to sort of to approximate the sampling, and you have the parameter, use that parameter to sort of solve the equation. So I was wondering, so do you have this kind of perturbation analysis? It's not exactly perturbation, but because your approximation using the architecture is not exact, you have some accuracy there. But you still use that as your solution of your equation. Then you have another accuracy in terms of solution of that. Is there any analysis about that, or right now just the observation?
It's an excellent question. It's an excellent question. We thought about doing this analysis, but we had to choose between working and other things like coping with much more general Hamiltonian, so we didn't do the analysis yet. But it is fundamental to get these results eventually. I totally agree. It's but we do not have it.
I see.
We didn't do it.
I see. But the other thing
is,
the other thing is also, you also mentioned the curse of the complexity of the M, right? Over there you have sort of the approximation theory about the neural network. Suppose you have the sampling data, you use how deep of the neural network to approximate that sampling data, then do that. So do you have like how expensive of this depends on? I mean, I gave you a depends on the initial data.
It will depend on the initial data and the Hamiltonian. That's why, I mean, let me be clear. Since you given an architecture, you can always find a Hamiltonian where you're going to lose, right? And then you say that architecture is terrible for approximating that class of Hamiltonians. Absolutely true. That's why we have not only one or two or three architectures, but we have more and more. And then we almost have the result, how to combine several neural network architecture into one, so that now you give me a Hamiltonian and say, well, if it can be well approximated by the first architecture, then the first architecture will do the most of the work. And then you have the other part that will not do. So this is what we are pushing. We can, I personally do not hope that one architecture is going to do the job excellently for everything. No, it's for subclass where they are doing a good job. And now it's a matter of growing the class by combining those neural networks together. Does it make sense?
I see. It does make sense. I see. So, but then this is sort of like the other question related. So this is like theoretically, suppose you have a different category, different initial guess based on this neural network architecture, you solve it, and then you say, I'm gonna for a different for a new input as an initial guess, I'm looking for the combination of the existing solutions.
Yep.
So how is there any is there any analysis say my sort of arbitrary initial guess could be like a combination of the finite or whatever? Like you have a space, then there's become a theory and so on and so forth.
Yeah, it's again, at the end of the day, we will need the result that you mentioned, the approximation theory. But right now, I'm thinking like that, like in optimization. In optimization, let's say you want to minimize the sum of two convex functions, f plus g. And you say minimizing f plus g is hard, and you say, okay, let's consider ADMM. What ADMM is doing? You're going to replace the sum by f plus the quadratic, and we call that proximal term. And then you have a catalog of proximal terms that you can compute efficiently.
Sure.
Now, if you cannot compute the proximal term point efficiently, then you're in trouble. So right now we are just trying to get this catalog and see how far, I mean, are they rich enough so that it is valuable to do the analysis. I mean, that's my personal perspective. It's limited resources, and I had to choose the thing. The theme. But I insist, those results that you mentioned are crucial eventually. I mean, if you don't have them, then you just like, hey, what is the error? What do you really compute? And if we do not have the analysis, then we don't know. And so it's not useful.
Yeah.
So right now it's more about what we can get without any error. And then
exactly.
Exactly.
I mean the concept, this is a sort of new concept, as you mentioned. Is like you basically write on the initial guess as a neural network. And what can you do? It's like a new way of representing data. So I have another small question. Sorry, I have so many questions.
No. Great.
So you actually encode the Lagrangian or Hamiltonian as an activation function in the architecture. Yes. So if the Hamiltonian, if the H is relatively complicated, L may not be easy to compute, then do you still, in practice, do you still need to use some sort of approximation, another neural network to approximate this activation, or how do you do?
It could be, because as you mentioned, the L that we consider for the papers are easily computable. But now it could be another neural network, another, I don't know, whatever. It could be another code. It could be the solution of an optimization problem, as long as it defines a convex
function. Then you unfold it as a neural network, something.
Yeah. Okay. So what's nice about this, graphical representation is that you can replace the box by whatever you want, a machine or nature to compute it for you. In practice, it is, of course, important to know how hard it is to compute those functions. I mean, there are many, how can I say, activation functions that we would love to put, but that involves estimating the value of an integral. and we don't know how to do that efficiently. So we're just like, okay, we don't talk about those guys. But yeah.
I see. That makes sense. Yeah, thanks so much.
Yeah.
This is really interesting.
Of course.
Thanks. All right. Any other questions, audience? If no question, that's the end of this talk. Thanks so much. Let's thank again for the speaker.
Thank you very much.
Thank you.